Hello everyone, welcome to today's lecture. And just as before, if you can, please turn on your cameras and ask me questions at any point. And I'm trying this platform EdSTEM and everything else for the first time. So if you have any feedback or suggestions on how it might be improved, please let me know. I'll try my best to incorporate them. I think you probably have more insights on remote learning at this point than any of ours because you've been through more courses. Okay, so just as an announcement, assignment 1 is up on the course website as well as on Gradescope as well as on EdSTEM, and it's due next Monday at 10 p.m. So there are 4 problems, 3 kind of theoretical questions. One question asked you to do some implementation and make some plots. You can use your favorite language for the last part. I just mentioned using Python because that's what there's some code available for plotting and stuff in the workspaces if you want to reuse it. Okay, any questions about the assignment or the logistics? Okay, if not, let's jump right into the lecture. So last class we talked about some assumptions that are natural and that we can make in the context of optimization, right? Smoothness, convexity, and then we use this to connect to analysis of gradient descent. And today what we'll do is finish the analysis of gradient descent and then hopefully talk about 2 other really important algorithms in machine learning, which is machine learning and optimization in general, which are Nesterow's accelerated gradient descent and stochastic gradient descent. So remember, this is a course on machine learning, but we've been talking about optimization for the last 3 lectures because, as we said, optimization is a fundamental way of tackling machine learning problems. You set up an optimization question and then you try to solve the computational problem. And gradient descent is one of the main ways. It's one of the main algorithms. So recall our goal from last class was to show a very nice bound on optimizing convex functions. So in particular, we said we're going to show the following. If a function f is beta smooth and convex, then gradient descent does indeed converge to the optimum, and it converges in a very nice rate. We can quantify it. It converges at this rate of 1 over k. If we ignore this beta and w0, w star, which are problem specific parameters, then as the number of iterations increases, you approach the optimum at the rate of 1 over the number of steps. So if you want somehow epsilon accuracy, epsilon closeness to the optimum value, then you have to do 1 over epsilon iterations, which is not too bad. And what we showed in last class towards analyzing this is 2 properties of gradient descent. The first was function decrease. We said that gradient descent with the step size of 1 over beta does indeed make some progress. It's not going to negate the progress that you're making, and it does decrease the function value a little bit. And it decreases at this current, with this bound at the very least. And the first bound did not use convexity, it only used smoothness of the function, right? And the second bound, which is distance decrease, was more specific to convexity and says as not only does the function value decrease, your algorithm actually makes progress towards converging to a global optimum solution. Right? So decreasing the function value doesn't mean you're actually approaching the optimum, right? Because you might just be stuck somewhere else. But this is saying you're making some progress towards the actual optimum optimizer. Okay, so today what we'll do is to use these properties to show our bound on gradient descent. Okay, so let's start with what else can we say going from here. And recall there was one more property that we had, right? This was the fundamental, what do you call it? Fundamental lemma of convexity. Right, so there is a characterization of convex functions in terms of the gradient. We said a function is convex if the tangent line at any point is completely below the curve. So if we specialize that to our values, we get right. So if we apply the inequality that we have for function values on the tangent line, we get this inequality, right? So one implication of this is the following. It says that okay, right? So now this guy, this minus delta f of k and wk minus w star, I want to use this to get a lower bound on how big the gradient is, depending on how far your point wk is from w star. Right, so function decrease tells you that you're making progress in decreasing the function, but it doesn't give me something very tangible because the bound itself depends on the size of the gradient at that point. So I need some other way to get a lower bound on the size of the gradient. And how can I do that from this inequality? How might I do that from this inequality? Does this ring a bell? Yes, no? So it's actually not, if you're familiar with Cauchy-Schwarz inequality, so we know that the inner product of two vectors is always at most the product of the two norms of the vectors, right? So we know that this quantity is at most right? This is because inner product u comma v, the absolute value is at most the 2 norm of u times the 2 norm of v, always. Right? The angle is at most the product of the lengths. Okay? Now, by the distance decrease property, we also know that this is at most the gradient times w0 minus w star. Okay? So let's call this difference from the true optimum as delta k. So our goal really is to show that delta k is very small as k decreases. Okay? And what we have from function decrease, so we are saying delta k is at most this much, and fd tells us that okay. So this in particular implies that delta k plus 1 is at most delta k minus this much. Okay, because I can subtract f of w star on both sides, and it's saying your distance to the optimum is actually decreasing by somewhat. But how much is it decreasing? I can bound it in terms of itself, right? So this tells me that delta k plus 1 is less than or equal to delta k minus 1 over 2 beta times okay, kind of mysterious, but it's saying basically if you're far from the global optimum, then you make more progress. Right? If delta k is big, then you're making quite a bit of progress in decreasing delta k. As delta k becomes smaller and smaller, you make less and less progress. right? It's some kind of recurrence relation, and we have to solve this recurrence relation in some way. Does this make sense? But remember, this is just like a number equation in numbers, right? It's saying kind of iterative equation. It's saying in the beginning, if your distance is very big, you make a lot of progress in decreasing it, and later on, you make slower and slower progress. Okay. So, can you elaborate a little bit on the last two things? So remember, delta k is the difference between f of wk and f of w star, right? And so we have this functional decrease inequality, and I can add f of w star on both sides, or subtract f of w star on both sides, and the same inequality would hold, right? So which would mean delta k plus 1 is at most delta k minus something, right? And finally, we have this lower bound on the gradient. The gradient is at least how far you are from delta k divided by the norm of w0 minus w star. So I'm substituting this equation here. Okay, does this answer the question? Okay, so now this is some numerology. You can there are many ways to solve it, but the main intuition is that if you're very far, then you make more progress, and that will give you enough of leeway to make the analysis go through. So just for brevity, let me denote this whole thing as lambda. Okay. So now, in summary, what do we have? We have this recurrence relation. Right? And now we do some simplifications for how to sort of go from here to the final thing that we want. Okay? And what does this tell us? It tells us that lambda is less than, or let me rewrite this. This is just some arithmetic now on some manipulations. Okay? So I just rewrote the inequality by moving some things around. And now this implies that lambda is at most. So recall that delta k plus 1 is less than or equal to delta k. We are only making progress at all times. We are only decreasing the distance. Right? So I can replace this with this much. Okay? Because it's only decreasing. Okay, right? So this is equivalent to saying 1 over delta k is less than 1 over delta k plus 1. Which is just so in other words, what we are getting is this sort of nice relation between the delta k's. 1 over the reciprocals are increasing in some substantial way. There's a question, does anyone have the link to the current live notes? It's just on page 4 of the notes. It's the same link, but you have to go to sheet number 4. I think it should be the same thing. Okay. So how can I proceed from here? Any suggestions? We are almost there. So we have this, the reciprocals are increasing. So what should I do now? And increasing in this sort of nice 1 over delta k plus 1 minus 1 over delta k is at least something. And what is our goal? Our goal is to just get a bound on delta k. Right? So what can I do? Well, this is a trick that gets used often in analysis of this sort of iterative algorithms. It's hard to compare what the iterative algorithm is doing to the optimum or to the beginning directly. So what you show is some kind of improvement in each iteration, and then you add up these iterations, these bounds. Okay? So for instance, what does this tell me, right? It tells me that lambda is less than or equal to this much, and in the same way I also get delta k minus 1, so on, right? Lambda is less than or equal to 1 over maybe delta 1 minus 1 over delta 0, right? So how can I use these inequalities together? What should I do with them?
You can sum them.
Right, just add them, right? So when you add them, we get something very nice, which is just lambda is at most 1 over delta k plus 1 minus, or there should be k plus 1 inequality, so I get k plus 1. Right, so I get k plus 1 by times lambda is less than or equal to, right, which is at most 1 over delta k plus 1, which in turn implies that delta k plus 1 is less than or equal to 1 over k plus 1 times lambda. Right? So that's what we wanted to show, didn't we? Okay. So that's what we wanted to show, right? You have 1 over k plus 1 times lambda, and just recall this guy was lambda was 2 beta times norm of w0 minus w star squared. It was just shorthand for that. We go up, that's what we defined lambda to be. Okay? Any questions about the proof? I mean, there is some arithmetic involved in the end, but I'd say the crux is you're showing that you're making progress at every step. If you're initially far, then you make substantial progress, and as you get closer and closer to the optimum, you actually make slower and slower progress. And this is something that actually happens that people see even in practice. Initially, you make substantial improvements, and as time goes by, you make slower and slower progress, but it's nevertheless something these things happen. Okay? Questions, Eric, and you note again where the k plus 1 came from. So basically, I have here k plus 1 inequalities, right? And I'm adding all of them up, all of these inequalities. In the left hand side, I get k plus 1 of lambda, and on the right hand side, something nice happens, which is that all of these terms kind of cross out. And this is a trick that gets used a lot in analyzing these optimization algorithms. This kind of telescoping thing happens a lot, and we'll also see it again later on when we analyze stochastic gradient descent. Okay? Any other questions about the proof? As I said, it's a bit mysterious, the proof, even if it's a sequence of calculations. You can fit all of them in a single page maybe, or maybe a couple of pages, but it is very influential. Alright, so let's summarize what we did so far. So summary, is f beta smooth and convex okay, which is kind of very cool. We have this universal style bound as long as the function is smooth and convex. And I would call this, maybe the second fundamental theorem of optimization. it's not an official term. I'm just making up stuff because there's no name for it, so I might as well, right? You might wonder what's the first if I'm calling it the second, and the first is really the analysis when the function is not smooth but just Lipschitz. That's a bit more complicated, and it gives a bound of square root k instead of k, which is another story. Okay, that I would call the first fundamental theorem of optimization. If you're interested in all these kinds of things, I have some references on the course website and also on the specific lecture on Edstein. Look at them and you'll get a good overview of what is known. So one thing to keep in mind is the following, right? So far I focused on gradient descent, but just let me remark that also works for subgradient descent. Okay, so what do you mean by also works for subgradient descent? You can define better smoothness in terms of subgradients, and if your function is better smooth and convex but maybe not necessarily differentiable, you can apply subgradient descent and you'll get the same bounds as before. In fact, nothing really changes in the analysis, everything is just the same. You replace the term gradient with subgradient and everything goes through. In some sense, the only property of gradient that we use is the lower envelope property, that the tangent line is completely below the curve, and that is true for subgradient. Okay? And the other thing is that this analysis also works for some non-convex problems. And this actually gets exploited, I've used it in my own research, as recently as last year, where we use such analysis, even not in the simplest form maybe, but variants of it, to analyze what happens for some non-convex problems as well. And the reason this happens is basically maybe your function is non-convex globally, wherever you are, but if in the region that you're optimizing it's convex, the analysis can still go through. Right? Imagine it's something like this. This function is not convex, right? But if my initial point is somewhere here, maybe you can still push the analysis of convexity, this gradient descent analysis, to go through. Right? These tricks kind of show up in, very recent papers as well. So that's something to keep in mind, that this analysis is not specific to gradient descent, and these tricks are very current even now, even though this is very, very old. Okay? All right, so do you have, we have something like this, some nice bound and so on. What would you want to do next once we have such a bound? If you want to explore this area, what are some questions that you might ask? Please ask the question that I'm looking for. How many iterations will it take? So we have some bound, right? I think what you really mean is, so we have a bound of 1 over k, right? It's saying if I want epsilon close to optimum, then I need to take 1 over epsilon iterations. And this is one algorithm that's doing it. But you might ask, is it the best you can do? Can you do better? Right? In the homework problem, you saw that if the function has some stronger property, then you can actually get much stronger convergence, that you only need log 1 over epsilon iterations to get epsilon close to optimum. Whereas gradient descent is just saying, you need 1 over epsilon iterations. So the natural next question should be, can you do better? right? So can you do better than this 1 over k convergence? Right? So now, if you want to ask such a question, we need to figure out what do we mean by can we do better? Under what assumptions on the function do we want to do better? If I have strong properties, a strong knowledge, or even stronger assumptions on the function, I can presumably do better, right? But if you think about gradient descent, it is extremely simple, right? It's not assuming much. It's only assuming knowledge or the ability to compute gradients of the function, nothing else. Right? It's not even asking, okay, what does the function look like? What is its value on certain point? Nothing. It's just asking for computing gradients of the function. And in optimization literature, there's a name for it, for such simple methods. These are called first order methods. So meaning I am trying to optimize some function f, but all I give you is some sort of subroutine which allows me to compute the value of the function at any point of my choice and the value of the gradient of the function at any point of my choice, nothing else. Imagine you're trying to do some deep learning training or whatever, but the data is sitting in the cloud somewhere. You don't get to see the data. All you get is every time you query, you get to know what's the loss function or what is the gradient, nothing else. Okay, so it's kind of a limited interface with the function, but it's also a limitation that we should respect because it often shows up in practice. Right? So first order methods means we have a subroutine to compute f of w or gradient f of w. Okay, I can't go and ask, okay, what is the second derivative of the function at so and so point. I can't ask, okay, is the function somehow like a linear function? If so, can you tell me what are the coefficients or anything like that? Does that make sense? So it's kind of a severe restriction that we're imposing, but we can ask under these assumptions, under this restriction, this restricted way of accessing the function, what is the best way to optimize the function? Is this 1 over k convergence the best possible? Does it make sense? All right, so let's take a 5-minute break, and when we come back, we'll see in the sense that I'll tell you really that gradient descent is in fact not the best way to design optimization algorithm under this first order method assumption. Okay, so let's take a 5-minute break, and at 10:35 we'll resume the lecture. All right, so we're talking about first order methods, right? We're saying you just have function, the ability to compute the function and the ability to compute the gradient, right? And for a long time, people didn't have, long time as in, people really thought about it a lot. And there were some special cases where they realized that you can indeed get speedups, or what are known in the optimization machine learning literature as acceleration. Beating this 1 over k convergence bound is sometimes called acceleration. And one of the landmark results in landmark algorithms really is what is called Nesterow's accelerated gradient descent algorithm, or NAGD. Okay, So this is from 1983. It was published in some Russian journal, but it's just really the algorithm is like 4 lines. Instead of gradient descent being 2 lines, it has maybe 2 extra lines, but it's amazingly influential in practice. In fact, many modern machine learning applications use some form of acceleration, even if not in the exact form as Nesterov envisioned it, just variants where you tweak the parameters in some ways. Okay, and I don't really have very good intuition for why this specific algorithm works or why this specific choice of the updates that we're going to see. And there are many papers written about trying to understand this algorithm, even though it's just 4 lines, because it's very mysterious. And I haven't found any of them really satisfactory. There's some ways of explaining it qualitatively, but it's really hard to say that, okay, this is the specific choice of updates that you should do for so and so reason. For gradient descent, there was strong intuition, right? Walking the steeper descent made sense. Nesterov's accelerated gradient descent, you can motivate it in some way, but then the exact choice is hard to motivate, I think. It's kind of mysterious, just magic and it works. That's okay. I mean, it's still simple enough for us to use it, even if it's kind of hard to get intuition for it. Right? So what is the idea behind it? And what does it actually show? We will see that basically NAGD gets the following guarantee. Right? So it gets the guarantee of k squared instead of k. So you're getting like a quadratic improvement on what plain vanilla gradient descent gets you. Right? So let me emphasize that even more here. Okay, so this k squared boost is why it's called acceleration. And as I said at the beginning, maybe in last lecture, a couple of lectures ago, the reason we'll look at these convex functions and things like that is that it's a nice test bed to design algorithms. And this is one of the cases where you see it in action. Like thinking about convex functions and trying to improve it from 1 over k is what led to this new Nesterov's accelerated gradient descent algorithm. And that now you apply it to non-convex functions and all kinds of other hacks on top of that. Nothing to do with convexity in the end. But the way you arrived at the algorithm, I think, is strongly motivated by studying it for convex functions. Okay, or even for something simple like quadratics. So what is the intuition behind, I wouldn't say intuition, but like at least some idea, some conceptual idea that goes behind this Nesterov's accelerated gradient descent. Right, so I'll get to the algorithm later on, it's just a few lines as I said, but the idea is the following. So you probably have heard of momentum, right? What is momentum? Suppose you're going on a straight line and you try to turn. Then you'll kind of veer away from this curve that you intend to take just because of the momentum that you currently have, right? So now imagine that you're doing some optimization, right? And we already saw that you can think of optimization as working on this landscape of the loss function, right? So we saw some simulations a while back where you could plot this surface and our goal is to get to the minimum point on the surface, right? So excuse me. So if you're So suppose our surface was actually like a parabola, like this, like a bowl, right? So then we start out from here. It made sense to just kind of if you just follow this sort of steepest descent idea, steepest descent, which is the gradient descent, then we get to the bottom of the bowl, right? So you can just kind of take a straight line all the way down. right? But now imagine this bowl is not like a perfect bowl, but has some weird distortions. Does it make sense? Like, it's kind of skewed in some ways than the other. It's very hard to draw a skewed bowl, but let me try to do something like that. It's maybe very curved here, and then it goes something like this. I don't want to like draw. Right, it's kind of skewed in some way, and it might not even be, in 2 dimensions it's even harder to see, but in higher dimensions the curvature could be in all kinds of places. And here what could happen is, just imagine you put a ball on top of this bowl, right? Think of this as some kind of well, and it is going to follow, get to the least position, right? It's going to go to the point eventually where the gravitational force is minimum, which is at the bottom of the bowl. But what sort of trajectory would the bowl take? What do you think? So when I put it at some point in the bowl, what would happen at the beginning? So 2 assumptions. One is you're really in a gravitational force. It's a bowl, and it's a huge bowl, and you're putting let's say a marble somewhere, and there is some friction or not. That's an assumption that, let's say there is some friction too. So what happens at the beginning when I put the bowl? Which direction would it start moving? Down, but I remember there's no specific down, right? On the surface, it's kind of weirdly curved. So which direction more specifically would it move? It's not, it's sticking to the surface, right? Down would mean like it could go in different directions in 2D. Which direction would it go? The gradient at the point that the ball was placed, right? Because that's where the force is acting, and that's how physics works. And you can see gradient descent also has this kind of nice interpretation in physics, right? If I put this ball, it would start moving in the direction of steepest descent, which is the gradient, right? So the marble would move in the direction of steepest descent. aka gradient. But now remember, we are in the real world. So the marble has some mass and there is some friction. So what happens as you keep going? It's very hard for me to draw this, but so let me try nevertheless.
So it will accelerate.
It will accelerate, meaning? So it starts moving like, maybe here the steepest descent is in this direction. Right, but the bowl is kind of curving all over, right? So what would happen as it keeps going? Like here, in which direction would it start moving? Which direction is the force pointing towards? So the force is basically acting along the direction of the steepest descent, which is gradient, right? But there is something countering the ball from moving only in that direction. And what is that?
Is it like other local gradients?
I would say it's more to do with the history. Like if I place the ball with 0 velocity at some point, it will always start moving along the direction of steepest gradient. But if I already have some velocity pointing in some other direction, what would happen? The direction of the next step of the gradient would be some combination of the next step, would be some combination of my current velocity plus the gradient at that point. Right? And the direction of the current velocity, the way it shows it quantitatively is with the momentum, right? If the marble has a lot of mass, then the momentum will kind of counter it. So somehow here, it will be some combination of the steepest gradient and the previous velocity, right? So as speed builds up, the next step depends on gradient at current point and current velocity, right? It depends both on current velocity and the current gradient. Any questions about that?
You think of this as almost like approximating some kind of like second order derivative, since there's like a history.
It is, right. And as you'll see, like it's almost like that, but you'll only use first order operations for it. So that's kind of cool about it. That's a good point. So somehow you're trying to exploit this fact that there is momentum, right? And intuitively, what does this momentum do is, if there is a consistent component of the gradient along some direction, right, that will keep building up. The ball is curving in weird ways all over, so the gradient is changing a lot maybe, but maybe there's always some small contribution in one direction, right? Then you keep building momentum along that direction, so it's hard for you to kind of veer away from that direction, right? And in function optimization also, people thought of using the same mechanism, right? So the way to interpret velocity is the change in your current position, right? So we're thinking of the position as the value of the function, and our goal is to get to the bottom of the ball, which is a global minimum, okay? So this is the landscape slash position is function value, right? So velocity is change in position. Oh, sorry, I should not say function value, but the current parameters, right? And change in velocity is change in position, okay? And the height is the function value. So you want to get to the bottom of the ball, so you're trying to minimize the function, right? That's the physics analogy. And so what kind of update would it tell you for WK plus 1? So previously in gradient descent, we said it was okay, WK minus some component times the direction of steepest descent, which was a gradient. If you want to take the momentum term into account, what should this update be? Now come up with your most natural guess.
Maybe adding the previous velocity.
Right, so you want to add, it should be a combination of the previous velocity and this. And what's the previous velocity? It's going to be some WK minus WK minus 1, right? That's the previous velocity. Velocity was a change in position, so it's going to be some combination of these things. Does it make sense? So what is the momentum here again? So the momentum is basically some constant times the velocity, right? Momentum is always the mass times the velocity. So the way we are changing our velocity right now is there is some update corresponding to, so maybe it's better to write it this way. WK plus 1 minus WK, which is the new velocity, right? Has some component coming from the force, from the direction of the steepest gradient, But then you also carry something of your current velocity going forward, right? Because of the momentum. So that's what this equation. So let me write it down. Some alpha times okay, does this make sense? It seems like a discrete process in which we stop and start. Exactly, right? Like, you can write this as a differential equation, but we are really thinking of dt as one time step of our algorithm. Right? So in a single step, something changes, and that's what we are writing. You should think of the time as like really small, then you can write it as a differential equation if that's something that you're familiar with. And there are ways of interpreting accelerated gradient descent as some kind of second order differential equation, but let's not go there. Okay. So, but where does the current velocity come from? Basically, we're interpreting velocity as a change in the previous position. And this is just the intuition, right? If you're trying to do it physically, you would write down some sort of discrete equations, and they would look something like this. And for some reason, people thought, okay, we should try and do something like this even for optimization. All right. Alpha here is representative of the mass of the object. Exactly, it's its ability to conserve momentum, right? So if it's massless, somehow you'd expect the force, like, maybe you should not think of gravitational force, but like, let's say it's electricity versus mass, right? So then, it would just keep going with where the force is pointing. Kind of forget where the previous velocity was, okay? This is just sort of rough intuition for how you might design some other updates besides gradient descent. Okay. Any other questions? And you can actually, if you're interested, you can do some physics simulations and see that it's really interesting what happens when you have a bowl with different curvatures and you see how this process evolves. If it's a perfectly symmetric bowl, nothing really changes because somehow the momentum, and the gradient, they all point in the same direction at every step. So you just kind of keep going along this line. Whereas if it's kind of weirdly curved, then you'll have some sort of, veering sort of spiralish trajectory. Right? And this is what it's trying to take. Okay? So that's the intuition. So this is called, taking momentum into account, you get other kinds of update besides just plain vanilla gradient descent. And what people observed a while back was that you can use this update to get faster convergence even for convex functions. Sorry, just for quadratic functions. That was known before Nesterov method came in. That if I take momentum, then, and your function was some kind of high dimensional convex function, let's say something like 0.5 times x1 squared plus 0.3 times x2 squared plus 0.9 times maybe x5 minus 7 squared and things like this, right? Here gradient descent has some convergence like 1 over k. Whereas if you take the momentum term into account, you can get 1 over k squared convergence, right? But people didn't know how to make it work for general convex functions until Nesterov's method came in, right? And there are as I said, there are various ways of interpreting Nesterov's method, but it's not clear what exactly, how he came up with those equations himself. Right? But let me tell you what the equations are. Okay. So the one thing to note in this sort of classical momentum interpretation is the way your velocity is changing is you take your current velocity and the current gradient, right? So somehow implicitly what Nesterov says is you have to first take a step along the current momentum where it takes you and then compute the gradient at the new point. It's kind of a weird system of equations, but it's just 3 lines. Whatever it is the following. So I start now with 3 points, u0, v0, w0, all are the same to begin with. And all the equations are like gradient descent. So I'm updating wi as kind of a gradient update, but not with wi. I'm doing it with vi, which is some intermediate thing, right? And ui is again being updated like a gradient, but I'm doing it weirdly with a gradient step at vi, right? And what is vi? It's some convex combination of these 2 points, right? So the way to think about it is vi is a convex combination of momentum and your previous velocity, and then you take a step along the direction and you compute the gradient at this point, and then you do something else. Okay? As I said, it's very mysterious how we came up with these 3 equations, but it's amazingly powerful. Any questions about them? So it's a little bit like gradient descent, and the main thing, it's a little bit like momentum because you're computing the gradient at a point which is a convex combination of 2 things. One is supposed to be the momentum, and the other is supposed to be the gradient. Okay? It's hard for me to understand or get intuitive understanding of these equations, but they're pretty simple to parse. It's just 3 lines of code as opposed to 1 line of update in gradient descent. Any questions about these 3 equations?
Just to double check I'm not missing anything, the only difference between the first 2 lines is a fixed eta versus a variable one?
Well, you're also changing this vi to ui, right? Like somehow
Right.
that's also subtle. Like somehow it's weird. Like I don't know how to interpret them. It's somehow you're doing 2 kind of gradient descents, but then you don't compute the gradient at the same points always. Like if you go back to gradient descent, right? When I update wi plus 1, you are taking the gradient at the previous iteration, right? But here you take the gradient at the convex combination of 2 points and use that to update the 2 gradient descent trajectories in some way. Okay. So it's kind of, as I said, it's hard to get some intuitive understanding of it, but it's simple enough to implement and see the amazing difference in practice immediately, actually. So which one is the momentum in this case? I say you should think of ui as kind of like the momentum.
So the step size associated with the momentum is like this increasing thing here, like eta I, you're increasing with I.
That's a
Like-
good question. So yeah, so that's sort of maybe I'm not sure what you should do qualitatively even. Qualitatively, yeah, I think
Well,
that's
I'm
what
just-
you should do, right? Like somehow you imagine that if you've gone, as you go further and further into the trajectory, you built up some momentum which tells you some information about where the optimum should be. Right, so maybe if there's some local dip which is pointing you away from the actual optimum, you don't want to lose that information. Maybe qualitatively that's one way to explain why it makes sense to increase the value of the momentum term as iterations go by.
So for later iterations, the momentum matters more for the update.
Or yeah, exactly. I think it's like how there's this joke about physicists, right? I don't know. There's a theoretical physicist and there's an experimental physicist, and the experimental physicist goes and says, okay, here's my data, explain it to me. Theoretical physicist says, here's the theory for it. And then the next day comes, oh, my data was completely wrong, it's the exact opposite. Then the theoretical physicist says, oh, then it's even easier to explain. And here's the explanation, right? So it's the same in this case. You can qualitatively justify increasing the contribution of the momentum term, which is that somehow you want to keep the histories, what you learned from the history, give it more weight. Okay? But forget all of this, right? It's a very concrete algorithm. It's just 3 lines of equations instead of 1 line. And there's a concrete way to set the updates. So for gradient descent, we just have one parameter, etas, that is same as here, 1 over beta. And then you have this eta i's and alpha i's, which are being chosen in some careful way. And you don't even have to do this specific ways of updating the eta i's and alpha i's. As I said, you can do some kind of binary search or grid search or things like that, and people do all kinds of tricks on top of that. And in fact, in most applications, you just use 0.5 and 0.6 and 0.7 or something like that. Don't even worry about these exact values. But what it did show was that you get this magical k squared with these 3 equations instead of the one from gradient descent. Okay, and hold on. So I might. In next class, we'll actually do some implementations and see how much faster it is. And hopefully you actually also saw it we'll see it even in your even in the homework. So if I do it for a quadratic function with some weird slightly skewed coefficients, this is what you see. The red curve is Nestrov's accelerated gradient descent and the green is gradient descent. Isn't it amazing that just 3 additional lines gets you such a faster rate of convergence? Within 10 iterations, it's so far ahead of gradient descent. Right? And this phenomena shows up in various places, and then you can use this to kind of design all kinds of tricks to go along. Hold on, where am I? So often what you do is, instead of just setting a fixed step size for this eta i's as shown here, you increase the momentum term as you go along in some qualitative way. And one way to interpret Nestrov's algorithm is basically some conceptual interpretation. Right? So one interpretation is basically somehow it's not exactly this, but if you wanted like a 2-line summary of something to keep in mind for the derivation, what you can say is somehow I define this new variable each time. Which is kind of like taking a gradient step, right? But then I move further along the step based on some kind of momentum. Okay, so maybe this makes it a bit more explicit on how the update is going. But as I said, there are all kinds of papers trying to analyze and explain, give some geometric intuition why this is the right thing, but it is what it is. Okay? Any questions about this? So unfortunately, I think going into the proof of this would be a bit too involved for what I have in mind in terms of breadth, covering things in this course. So if you're interested in the proof, it's maybe a half a page of more calculations compared to what we did for gradient descent. Kind of follows the same sort of inequalities, and the best place to look for this might be the survey paper that I linked on the course website, not on the course website but on EdStem, and it gives you a very nice analysis of the 2 methods, gradient descent and Nestrov's accelerated gradient descent, in some unified way. But I won't be covering in this course. Okay? All right, so now we know something faster like k squared, and this is also a first order method, right? Because we are only looking at the gradients. In fact, you're only computing one gradient, right? You're still only computing one gradient per iteration. You're just combining things in some weird way. Okay? And so this is also a first order method. And you might now ask, okay, I got 1 over k squared, but why not 1 over k cubed or something like that? So if this 1 over k squared doesn't seem that impressive, just think of what happens if I want to get accuracy which is 0.01. Then with gradient descent, you basically need 1 over epsilon iterations, which is like 100 iterations. Right? With Nestrov's accelerated gradient descent, you only need 1 over square root of epsilon, which is 10 iterations. Right? So GD epsilon close to optimal needs 1 over epsilon iterations. NAGD 1 over square root epsilon. Right, so if your accuracy is 1%, then there is like almost a factor of 10 difference. Okay, and you could see it even in that toy plot that I showed for a simple quadratic function. And hopefully you'll also see it in the logistic regression problem from the homework. But you might ask, is this the best you can do for first order methods? And it turns out that this time, Nestrov actually and others showed that with first order methods, that is indeed the best you can do. It's quite non-trivial to formalize this and prove it, but it's something to know that if I want to get epsilon accuracy with only first order methods, you need at least 1 over square root epsilon gradient evaluations. That's what this lower bound means. That you need to run at least k, after running k iterations, you cannot get better than 1 over k squared accuracy. The flip side of that, the contrapositive, is saying that if I want epsilon close to global optimum, then I need to evaluate the gradient on at least 1 over square root epsilon points. And if the only thing I can do is evaluating gradient, that's the best. Okay? So Nestrov's accelerated gradient descent is the best possible if I'm only looking at first order methods, even for convex functions. And you can teach a semester long course just on all kinds of other variations of first order methods, each of which has its own sort of pro and con. So k here is number of iterations. So maybe let me write it this way. 1 over square root epsilon iterations is best possible to get accuracy epsilon. So there's a theorem which tells you that if you want epsilon accuracy using a first order method, then you need to query the function at least 1 over square root epsilon points. You need at least 1 over square root epsilon gradient evaluations. Okay? All right, so now, is this the end of the story for gradient descent? What do you think? Well, it turns out that it's not quite the end of the story. And let me segue away from gradient descent and Nestrov's accelerated gradient descent and talk about something else altogether, okay? But related to gradient descent. So, in the next lecture, we'll look at the applications of all these kinds of gradient descent for some specific ERM problems and see how they fare. But right now, let's also look at one more very important variant of gradient descent, important in the sense that it's very important in practice. And once we have this variant, you can combine acceleration and things like that, in all kinds of, just throw them in the mixing bowl and see what happens, implement it, and see what works. That kind of stuff goes on all the time. But what is this third variant, and why do we even, why would we even think about it? Okay. So gradient descent seems great so far, right? Gradient descent and Nastrov's accelerated gradient descent seem great. They have very, they only need the computation of the gradient of the function. And they get some pretty good accuracy, pretty good guarantees for optimizing smooth convex functions. And even for non-convex functions, if it's smooth, we know that we make some progress all the time. But now let's go back to our original motivation for studying optimization. And what was our original motivation for studying optimization? For this class, what was the motivation that we started out with?
Learning.
Learning, right? So which was empirical risk minimization, right? So we had this sort of loss function. Right, so we said, okay, learning for us is just going to be about solving this empirical risk minimization problem, right? So let me make one change, I think, which is the one I should have used in the first lecture itself, but it's a minor change, which is to normalize this loss function. So it's not just the sum, but it's kind of the average loss, right? It's 1 over n. I'm scaling it up so that you have some kind of baseline to compare with. Okay? This is the function that we're trying to optimize for. And now imagine, let's try and see what happens if I want to run gradient descent on this, right? So what's the cost of such a thing? What is the gradient of this function, What is the gradient? What would I get? Insertions. It's a simple enough function, right? ERM is simple enough that we can compute the gradient pretty explicitly. And the cool thing with gradient is that it's kind of a linear operation, right? The gradient of sum of two functions is
Like the sum of the respective gradient.
exactly, right? So it's just sum of the gradient. So even though this looks like some complicated function which depends on all of the things, I can sort of compute it individually, right? Which is a very nice thing, nice feature of gradient and hence of gradient descent. And now I can even use a chain rule, right? Recall the loss function is just a bivariate function, right? So this was just from something like r times r to real numbers. So if you want to use the chain rule, what would I get here? So the function w is inside, right? So what would I get if I use the chain rule here? So let me write it down. So I would take the derivative of the function L with respect to the first variable, right? Because the second variable yi doesn't depend on w. So I'd get something like, so I'm thinking of this as a function of L of a comma b. I'll take the derivative or the partial derivative with respect to the first coordinate. And then what should I multiply this with? Right? So I just have to compute the gradient of the parameterized function, parameterized family at a specific data point xi. Right? There's this nice sort of decoupling that happens here. I just need to evaluate the parametric family at xi and need to evaluate the gradient at xi. Okay? So in terms of time complexity, how much time does it take to compute the gradient here? How much time to compute gradient? Tell me a lower bound. Suppose there is an oracle which gives me the gradient hw of xi at any point. It's just a function, count that as a constant operation. How much time do I need to compute the gradient of the overall loss function?
N queries, that would be.
Depends on the type of the inner functions times n, right? It's not just the type of the inner function. Even if I tell you that computing this is just unit cost, I still need to add up these high dimensional vectors, right? So as someone said, you need to make n queries, and it's not just the queries, but also I need to add up all of those things, right? So it's O of nd plus time for individual gradients. Okay? So at the very least, it seems like you are taking n times the dimension much time per iteration, right? And now if you think of modern data sets, right, n is almost like millions of pictures. You're training your deep neural network on a database of images, which is huge. And what is the dimension, right? These images are, let's say, HD, which is 1024 by 1024. And that's again another huge number of dimensions, right? So even to do a single step of the gradient would be prohibitively expensive for many data sets, many large data sets. So what should you do in that case? What can you do in that case? So for many modern data sets, n time d per iteration is bad. Makes it really infeasible. So what can you do in this case? Excuse me. So take mini batches, that is sum over m, where m is much less than n. So the idea really is, if you think of gradient descent, the analysis and everything else that we do is pretty robust in terms of doing, in terms of the fundamental principles. Which is, what is the idea, right? So we said, I want to get the most bang per buck. So I started moving along the direction of the steepest gradient, steepest descent. But what if I don't get access to the steepest descent, but which is something approximately like the steepest descent? I might as well, I could potentially try that instead of moving along the gradient, right? So that's the main principle behind what is known as stochastic gradient descent. Or SGD. Right? So the idea here is that maybe I don't get to compute the gradient exactly at every time step, but I might have some kind of an estimator for the gradient, something that gives me some approximation of the gradient. So what do I mean? So we have an estimator. Let me write it as G of W for the gradient. Oops. Okay, so G of W is an estimator, meaning it is a random variable. Now you use some randomness or whatever, but I'm getting something which is an estimator for the gradient, and we'll assume in statistics language it's called an unbiased estimator, meaning the expected value of my estimator is exactly the gradient. Actually, let me switch from working with loss to any function. Okay, so I'm saying, maybe I don't have access to the gradient exactly because it's taking too much time for me to compute the gradient, but I have some kind of sense of what the gradient should be. So imagine every one of you is like a data point, right? So every one of you contributes something to the gradient. So instead of getting input from every one of you, what's a quick way of getting an estimate for the gradient?
Just sample, maybe.
Just sample, right? I'm going to pick one of you at random and ask you, okay, what's the gradient? Right, that's it. That's my estimate for the gradient, and that's what I'm going to use in my algorithm. Okay, so what is SGD then? It's the exact same thing as gradient. What you say is okay, so that's the stochastic gradient descent algorithm. That's it. So it's the same thing as gradient descent, but suppose I'm trying to optimize some function f again, and instead of computing the gradient exactly, instead of using the gradient exactly, I'm going to use an estimator for the gradient at the current iterate. And now notice that this is a randomized algorithm. This is not a deterministic algorithm, right? Okay. So now let's think of for gradient descent, we had some good sense of when the algorithm was working. For Nesterov accelerated gradient descent, we also had some sense of when the algorithm was working, right? Like we had this rigorous bounds and analysis for convex functions. Now you might ask, okay, I want to do something like this even for stochastic gradient descent. What sort of guarantees does it have? Does it work? If I use just a simple estimator for the gradient or any estimator for the gradient, would it converge to the true optimum? Right? Once again, we ask these questions because we want to improve what we can about the algorithm. Right? So if the only thing I told you was that the expectation was the gradient. But what else can I do? What else do I need to know to get a good sense of whether any suggestions? There are different kinds of qualities of estimators, right? You can think of the estimator as some kind of survey that you're conducting. And we all know that pollings can be very off, right? But imagine someone asked me how many samples or how good the quality of the estimator is. Again, let's kind of sort of dissociate the problem of stochastic gradient descent from the exact question of how you're getting the estimator, right? From empirical risk minimization. So for instance, if someone told me, if you ask me what's your prediction for weather today, maybe I can say, okay, with 60% probability, the weather is 120 degrees and 40% is 0 degrees. Okay, so I'm right in expectation, but this is an awful prediction, right? Whereas maybe you say, okay, 90% it's 80 and 10% it's 70. That's probably a better prediction, even if the expectations are the same. So what's different about these two predictions? How can I judge the quality of an estimator? What's a measure that you would think of if you want to judge the quality of an estimator? The variance, right? So, but remember here, this is like a multivariate random variable. So g of w is a random variable. So how do I define the variance? So the variance of the estimator is an important parameter when we think of gradient descent. Okay, and the way it's defined is kind of, the most natural thing that you can imagine, which is that you look at how far each sample is from the true expectation. Right, so this is really for any vector value random variable. I'll look at how far each sample is from its true expectation in the length squared. Okay, so that's the definition of the variance of a vector value random variable. Kind of looking at the variance of each coordinate and adding them up to get the total variance of the vector. Okay. So now, surprisingly, stochastic gradient descent also works very well on convex functions as long as you have some kind of good estimator. So what do you mean? Plus, you basically get something like that we had before. Okay. So what this is saying is, okay, stochastic gradient descent also gets you something which is not too bad. So maybe let me write it properly. Okay, so it's almost like gradient descent, except that this added term corresponding to the variance that your estimator has. Right, so in some sense, if I put the variance to be 0, I recover the guarantee of the usual gradient descent. Okay, whereas what did I okay, hold on. Okay, so if I set eta, if I have 0 variance, then I get the same exact guarantee as gradient descent, which makes sense. right? So stochastic gradient descent is really doing as well as gradient descent, except for this accumulation of this eta sigma squared, right? And now you kind of get into the game of what should this right eta be and so on, and you can balance it and you set it to be something like 1 over square root k to get the right bound actually. Okay, so let me now say something else. So let's go back to ERM. So recall our function was this guy. Right? And we also said the gradient was this much. Okay? So what's the natural estimator for the gradient here? If I don't want to compute the gradient exactly. So as we said, computing the gradient means that I have to look at every data point in my data set. Whereas, maybe I can get away with only looking at a few points. Right, so what's a natural estimator for the gradient here? And I think some of you already answered it. Said, take samples or take mini batches, right? What does it mean? Basically, here's one estimator. Pick a uniformly random I and output okay. This is an unbiased estimator for the gradient of the function at W, right? Instead of looking at all the data points and their average, I just pick one at random and then output the gradient at that point, of the cost function at that point. But this is really a stochastic gradient descent, and this is the real algorithm that gets used in most ML training applications these days. And variants of it. Okay, so one of the things that people do is, you don't take just a uniformly random I each time. You just reorder the data set once for all at random completely, and then you just keep computing the gradient by looking at each point one after the other. People also try to look at mini batches where I don't just take a single point. I take maybe some 10 points, 20 points. Most people use something like 30 or something, that's the limit, 30 samples, and then compute the gradient and average on those 30 points and things like that. Okay, so, and now once you have this kind of gradient estimator and stochastic gradient descent, you can also define Nesterow's accelerator stochastic gradient descent for what it's worth. You just replace the gradient in Nesterow's algorithms with estimator for the gradient there. Okay? And in the next lecture, when we come back, we'll try and show this theorem, try to understand why stochastic gradient descent does or still does well as gradient descent. And you'll see that it's kind of pretty easy to modify the analysis of our algorithm to see this guarantee. And one of the reasons I want to do this analysis is that there's something mysterious here. I didn't write down WK as my final guarantee. If you look at WK, that often doesn't give you a very good bound on the final function value. You have to look at something else. And we'll see why inner analysis in the next lecture. Okay. So our goal for next lecture will be to finish the analysis of SGD and then look at applications of all three methods for some real learning problems and see how they fare against each other and how they fare in the general context of solving the learning problem that we're interested in. All right? Okay. So I'll see you all on Monday, and remember the homework assignment is due on Monday, and I have office hours today from 12 to 1. Bye everybody, see you on Monday.